Okay, let's consider the following source. I'll take ABC, DEF, where probability of A is equal to probability of F, which is 0.1. Probability of B equals probability of E is equal to 0.15, and probability of C equals probability of D, which is 0.25. So let's firstly quickly check to make sure this adds up to 1. 2 times 0.1 is 0.2, 2 times 0.15 is 0.3, and 2 times 0.25 is 0.5, 0.5 plus 0.3 is 0.8, plus 0.2 is 1. So this is a valid probability. Let's now calculate the entropy. So I have 2 times log 2, 0.1 times log 2, 1 over 0.1 times 2 for those two, plus 0.15 times log 2, 1 over 0.15 times 2 for these two, plus 0.25 times log 2, 1 over 0.25 times 2 for those two. Okay, what's this term? This term, what's log 2 of 1 over 0.25? 2. 2 times 2 is 4, times 0.25 is 1. This is 1. What's log 2 of 1 over 0.15? Nobody knows, honestly. Just off the top of my head, it's 2.737. Thank you, MATLAB. Okay. 2.737 times 0.15. Actually, let's combine the two. That'll make this easier. 2 times 0.15 is 0.3. We multiply that, we get 21, 9, 11, 21, 22, 6, 8. By that, and we have 1, 2, 3, 4 decimal places. Oh, good. Okay, so this is 0.8211, and over here, log 2 of 0.1, 1 over 0.1, 3.322. So times 0.1 is 0.3322 times 2 is 0.6644. So we have 0.6644 plus 0.8211 plus 1, which makes 5, 5, 8, 4, carry the 1 is 2, so 2.4855. So basically, just less than 2.5. Let me write that over here. So, there exists a prefix code. Well, what's the maximum penalty for which there must exist at least one prefix code? So, that's right. So the maximum penalty, we said this last time, there must exist at least one prefix code with length between entropy and entropy plus 1. There must exist at least one prefix code like this. So the Huffman procedure, because the Huffman procedure finds the optimal prefix code, we must be able to find one with length less less than or equal to 3.485. So let's check and see how we do. Okay, actually I'm going to erase everything. Now, we know this is not dyadic, so we will not achieve entropy, but let's see how bad it is. Okay, what are my two most likely source letters? I erased everything, but I wrote it down. Most likely, so I'm going in C and D. Probability 0.25 each. Then I have B and E, probability 0.15 each, and A and F, probability 0.1 each. By the way, ties don't matter. They will affect the structure of the code, but they will not affect the average length. When you combine source letters, there is a rule, which actually I can't remember off the top of my head, but there is a rule so that the variance of the length. So I mean, average length doesn't change. The variance of the length might make a difference. If the variance of the length is high, that means many of the code words are long or short. They're not really close to the average. So there is a rule for combining letters and how to resort them if there's a tie, so that the variance of the length is shrunk. But I can't remember what it is off the top of my head. So. But for now, we will just say it doesn't matter how you resort if there's a tie. I don't think we'll actually hit a tie here. Okay. Anyway, what do? We combine A and F. What's the probability of those two? In total is 0.2. So where does it go?
It goes above 0.15.
That's right. So we resort like this. Those stay on top. These go here, so I have AF, and these go down. And I'll assign this one a 0, and this one a 1. Okay, next stage. Combine these guys. What's the combined probability there? 0.3. So where will those go? They'll go on the very top. That's the most likely letter now, is B. Let that be 0 and that be 1. This one goes down. This one goes down. Down. Now we combine DAF. Total probability 0.45. That also goes on top. This goes down. This goes down. Combine these two. That'll go on top. BCE, 0.55, and DAF, 0.45. And finally, we combine those two. And that's the end. Okay. So, in this case, we actually had to do some resorting. We had to think about where the combined source letters went after we combined them.